everybody. I'm Alejandro Ranchal-Pedrosa, and I'm going to be talking about how we are providing faster finality for Filecoin and verifiable proofs for interoperability with chains. So this is the outline of the presentation. First, a little bit of the status quo of expected consensus, the implications that fast finality will bring, or are going to bring, or are already bringing to Filecoin. Our first step into bringing faster finality that we call the easy finality calculator, that brings down finality from hours to minutes, tens of minutes. That we wanted even more faster finality, so we look at more core protocol changes. So we'll explain some of the architectural options we looked at and why we settle on what we call F3, which stands for fast finality in Filecoin. The core of F3, there's a new consensus protocol that we call GossiPBFT. We'll also justify the need for this new consensus protocol and its the good stuff that it brings, and explain a little bit of the protocol, and also what we call the finality exchange protocol, which is the protocol that that on top of the fast finality that GossiPBFT brings in F3, it builds a succinct verifiable finality certificate to be used outside for to prove finality for people that are not running full nodes, so people running outside of the system. And then the roadmap of the projects. So first, expected consensus. So expected consensus is the longest chain consensus protocol at Filecoin at the moment, because it's a longest chain type of protocol, or heaviest chain type of protocol. Finality comes from the growing confidence in a block, or in the case of Filecoin, a tip set, which is a set of blocks that share the same parent tip set in the same epoch. Well, in Filecoin, time is discretized into 30-second slots that we call epochs. So yeah, the finality in expected consensus comes from growing confidence over time that a reorg happening, bringing that tip set out of the heaviest chain, is less and less likely. So that's how finality comes. In the case of, in a longer chain type of protocol, there's no necessarily a prescribed finality time, like in Bitcoin, that recommends 6 blocks, but the confirmation time is up to the user to decide. In the case of Filecoin, because the power table is part of the state of the system, and the power table is assumed to be final by the Filecoin clients, by the implementations, there's actually a prescribed finality time, so kind of an upper bound for the applications not to wait more than that, and that is 900 epochs, or equivalently 7.5 hours. So 7.5 hours, or some application could take less, but exchanges take 100 minutes. It's just a huge pain point on a product blocker for the Filecoin ecosystem. So, last year we released the Filecoin virtual machine, and now a bunch of applications can be built on Filecoin, but there's so many that are not willing to wait this much for anything, right? Now IPC, Fluence was talking about IPC. It's great that you can launch your own, even your own token and your own chain, basically, like subnet, but still any deposit, any withdrawal, any interaction with any smart contract in the main chain or with other layer 2s are going to need to pass through the main from the main chain through Filecoin, and they're going to need to wait this amount of time. So it's a huge pain point. And also, of course, also interoperability through Axelar or some other chain bridges is also going to suffer from this long time to finality. That's why we look at faster finality. So here's a very simple example for perhaps somebody who's not following everything. So very, very simple. Bob tries to deposit 4 fields into some exchange, whatever is his favorite exchange, and all of these exchanges, when you deposit field, required to wait 100 minutes. But it's just a deposit, but still it's a bit annoying even for Bob, right? Even if it's just a deposit for some change. So the first thing we did is try to be smart around it, and what can we do without making any big change that's going to take a long time to come into the core protocol? So that's what we call the easy finality calculator. The easy finality calculator provides finalization within tens of minutes in the good case, and it is no upgrade of Filecoin. So any application can already run. Just looking at the information that's readily available, it can already finalize tip sets within tens of minutes in the good case. But on top of that, we are building F3, and F3 will provide finality in tens of seconds. It's coming soon, probably end of Q2, beginning of Q3. And it will also provide succinct verifiable certificates of finality. That's why we think that the F3 is a game changer for the Filecoin ecosystem. So first, easy finality calculator. How can it be that we provide faster finality without any changes to the protocol? Well, for that, the first thing we did is, why 900 epochs in the first place, right? So we went back to the docs, to the history books of Filecoin. Where does this 900 epochs number comes from? Well, it turns out that it comes from assuming the worst case because they wanted a static value that they just embed like an absolute value that considers the worst asymptotic case. And according to their analysis, that was 900 epochs. And that is true if you assume the worst case. 900 epochs is a very safe value. But what if you can have a look and just, realize that not all situations are the same? So the easy finality calculator comes from the principle of not all tip sets are created equal. So the amount of confidence you have in a local view of your heaviest chain when the last 5 epochs of the heaviest chain only contain 2 blocks per tip set. In Filecoin, in expectation, there are 5 blocks per epoch. So if you see only 2 blocks in your heaviest chain, the amount of confidence you have in this tip set is not the same as if you have seen for 5 consecutive epochs, 5 blocks in 5 consecutive tip sets. Of course, you have a lot more confidence in that other tip set if you have seen 5 blocks per tip set for a long time. So that's kind of the principle. It turns out like, Filecoin normally works well, synchrony occurs, and you more often than not have multiple consecutive tip sets with 5 blocks, with 4 blocks, 6 blocks. So in most cases, if you use this information, the fact that you are in a pretty good case, you can actually bring down the finality time to just 30 epochs, which is 15 minutes. So it's a 30x improvement with respect to the absolute worst case value. And it all can be done just with your own full node, with the information that your full node already has. We proposed the design of this finality calculator in an FRC, the Filecoin Improvement Proposal repo, and it has recently been merged. I think it was this week. And we are also working, frankly, we just haven't found the time to work on it, but it will probably take 2 or 3 weeks of some core dev doing this. And we want to, even if you can do it on your end as an application, we are working on providing an API call, so just the raw functionality that provides the probability of a block or a tip set suffering a reorg based on information that the node can see. But as I said, as an application, you can already have it yourself if you want to. Just to explain a little bit of how the analysis comes from, although the details are in the FIB repo. So we discretize time into 3 parts. The first one is the distant past. So it's everything, so all the time that passed from the beginning of Filecoin up until the tip set that we're observing. So the tip set that we care for in terms of finality. Then the recent past, which is everything that happened between the observed tip set and the current epoch, so the current time. And the future is whatever may happen from now to the future. So of course, for the future, we assume the worst case because there's nothing we can know. For the distant past, there might be some delta depending on how far in the past we're looking. And for the recent past, we have like very available information as long as the observable tip set is not that far in the past. But again, the details are in the FIB. And then here are some results. So if we look at the green plot is the 30th law moving average of the blocks per tip set. So we see on the first 3 quarters of the plot, more or less on average, there's like 5 blocks per tip set. So it's kind of like the best case scenario. And then towards the end, it drops to like on average 4 blocks per tip set. And that's when the error probability, the blue plot, kind of like grows. So, it's easier. So it's probably, so the confidence you have in not suffering a reorg that puts that particular observed tip set outside of the heaviest chain, kind of like, so the confidence you have like lowers, like you have less confidence in that tip set as a result of seeing less blocks in the 30th law moving average. So going back to the simple example with Bob just depositing some fields in some exchange, we bring in the good case, the worst case of 7.5 hours for finalization to 15 minutes, which means that if exchanges were already happy with 100 minutes as a static value, in the good case, they will be happy with just 5 minutes. So this is a massive improvement, right? Hours was really bad, especially since we had the Filecoin virtual machine. Minutes is great, it's so much better, and it can be done already by any application, so that's great to have 15 minutes for finalization, but we want better. We want even better. In particular, we want seconds, and we want to be able to prove this to people that are not running full nodes. However, we cannot reach the lower bound of finality when you're running a longest chain type of protocol. And even some longest chain type of protocols like Ethereum that have provided some finality gadgets, some newer architecture, still take about 5-6 minutes for finalization. So what we need is a new architecture. But let me justify it even further. So we set up 4 goals for this project. we want fast finality, but we don't want fast finality to come at the cost of less robustness, right? You can always get that. You can always get faster finality with less security if you just lower your requirement and you just like finalize faster. But that's not kind of the goal that we're setting. Normally, another point that suffers when you want fast finality, but so low latency, but high security is your assumptions get stronger, right? You have a weaker adversary or you assume synchrony. We also don't want that. Or put differently, we don't want this project to be the reason. So we're designing this as modular as possible. There might be other parts of the system that might change later on. So we don't want to be this module that we're designing to be the reason why the system has strong assumptions. There might be other reasons why the system has it, but we don't want this module to be the reason. And we're doing this in the context of providing faster finality for an existing system that has been running for years, that has a strong community behind. We don't want to make huge changes, right? We want to follow the path of least resistance. So with these goals in mind, we set out to look at the state of the art. And here's a kind of like a very summarized explanation of some architectures that we looked at. So fork choice protocol already said, not fast enough. They don't do the job of tens of seconds for finality. When you're looking at fast finality, one of the architectures that strikes out is Avalanche's subsample voting, because it's extremely fast. Like it can finalize things within a second, and it scales very well. So it's kind of independent on the size of the number of participants, but it has strong assumptions, particularly strong synchrony, and it tolerates an adversary controlling at most 20% of the power table. Actually, 20% is not that bad when you have a huge power table and you have to resort to committees. But we believe for the power tables that we're talking about for Filecoin, within the 3,000 number of validators, we can do better than 20%. And then I also talk a bit about Casper's FFG, so best effort finality gadgets that are already being proposed. They have the advantage of having a small refactoring because it's just an added module that you plug in. But in the case of Casper's FFG, I particularly have not seen any proof of security or correctness. So there's some security concerns, and actually some attacks have been found that have led to some changes to the initial proposal. And it also still assumes a strong synchrony, and it still takes 5-6 minutes for finalization in Ethereum because it depends on synchrony to be finalized. And of course, the holy grail of distributed systems that have been studied for decades, BFT protocols, we know they're fast, they're resilient, but it will be too much refactoring, right? Changing a longer chain type of protocol into a BFT protocol. So then looking at the last two, you got the advantage of a small refactoring from the finality gadget, but then fast and resilience of BFT protocols. So why don't we then combine them? So that's exactly what F3 is. F3 stands for fast finality in Filecoin, and the F3 component at its core essentially runs. So it's a module that is plugged in, kind of like the finality gadget of Ethereum, but at its core, it runs a new BFT protocol. So we get the fast and resilience of BFT protocols, but we don't need to do that much refactoring on the system itself. So on the architecture, here's a very simple schematic of how Filecoin works at the moment. So very simply, some blocks come from the network onto a process that we call the easy syncer, and the easy syncer adds blocks to the local view of the chain that the node has, and then there's some fork choice rule that selects the heaviest chain. And what we do with F3 is that we add a new separate component that reads the heaviest chain, the head of the heaviest chain, the local head of the heaviest chain, and it proposes it as input to the BFT consensus protocol that we call GossiPBFT. Then this instance of GossiPBFT runs, it terminates, it outputs some block that everybody agrees as final, so the new head of the finalized chain, and then this new head is checkpointed in the local view of the chain, meaning that every heaviest, so the new heaviest chain will always extend the prefix up until this new head of the finalized chain. In terms of the integration, so the changes that need to be done, good news is on an abstract level, the functionality was already there. So we essentially, the only thing that we absolutely need is to be able to read the head of the heaviest chain according to EC, and to be able to checkpoint a tipset, so to mark a tipset as final. And this is functionality that Lotus already provides, the Filecoin client already provides. But when we set up to implement this for practical purposes, we did some changes. So particularly, we don't just call the API function to checkpoint a tipset. We rather just modify the fork choice rule to directly provide this functionality. And instead of having F3 reading the head, for some reasons that I'm not going to get into, we prefer to have Lotus or EC to push every change to the head, just because it's faster to run F3 this way. And there's also this more fundamental thing that BFT protocols, partially synchronous BFT protocols favor safety over liveness, whereas long chain protocols favor liveness over safety. And we made the decision of following the path of least resistance, meaning in the catastrophic scenario that probably will never happen, that you have to pick it between either between safety or liveness. In this case, the longer chain protocol rules over F3, so we will just favor liveness and kind of like fall back into the finality that we had before of 900 epochs. For that, of course, there will have to be one instance of GossiPBFT that takes 7.5 hours to terminate that. Again, we don't expect that to ever happen. And of course, we need to implement all the code for GossiPBFT, but that can be done completely independently as a new module, so we don't need to make any modifications onto the existing code. And GossiPBFT, the good news is a quite simple protocol to implement. It's not very elaborate. It doesn't have like a very complex view change like PBFT or nothing like that. It has some elements from PBFT that has the name. And it also has a lot, so it inherits a lot of ideas from a very old protocol proposed by Gracha for binary Byzantine agreement, a synchronous binary Byzantine agreement decades ago. So it's, it's founded on very well-known and battle-tested protocols. But we argue that what we propose is way better than those, and that other protocols in the state of the art for some of the reasons that I list here. So coming back for the 4 goals that we had set out for this project, weak assumptions. So GossiPBFT is resilient optimal and partially synchronous. We don't need to assume synchrony for safety. Simple protocol is completely leaderless, meaning every process runs exactly the same code. We don't have designated roles like leaders or anything like that. It runs in rounds, and every round has 4 steps. All of these steps are very similar, so they have the same message format and very similar message validation and logic. And we have decided to be robust to Eclipse attacks, denial of service attacks. And in the particular case of long-range attacks and censorship attacks, we have decided to be resilient against a 66% adversary compared to the classical 33%. We will get into that in a minute. And in terms of fast finality, meaning low latency in the case of a BFT protocol, we only need to exchange a linear number of lead P2P messages for termination. Each of them have linear size in bits. There are workarounds to have constant size in bits with some of the trade-offs. And if we use committees, then we'll have a constant number of messages being exchanged for a termination of one instance. And in the good case, we can actually terminate in 3 to 4 asynchronous steps. And actually, we're working on optimizations. We can probably terminate in just 2 steps in the good case. And this will be the 2. So these are the fundamental step in the good case, right? If we get lucky, suppose we have a power table with 4 nodes. One of them is Byzantine. In this case, this Byzantine just doesn't communicate with anybody. And so with the other 3, we can make a strong quorum, so 2/3 of the power in order to terminate. If we get lucky and everybody proposes the same block to finalize, then in the prepare step, they all propose this block. Everybody sees a strong quorum of prepare messages. They propose the same block for the commit step. Everybody sees a strong quorum of messages for the same block in the commit step. We can terminate. We have, however, added a new step that we call decide. So prepare and commit run in every round. If we don't get lucky, we need to execute more rounds. Decide only executes on termination, so it doesn't run in every round. And the purpose of decide is twofold. First one is to provide resistance against long-range attacks in the presence of an adversary controlling up to less than 2/3 of the power table. We could use commit to terminate, but then we will tolerate an adversary controlling up to 1/3, not 2/3. So it's a huge improvement in terms of tolerance against long-range attacks, which becomes even more relevant when you're generating finality certificates within seconds. And the second one is to actually have a dedicated step to aggregate signatures into whatever we need for the finality certificate, which might not be the same, which is not the same as what we need to try and terminate the execution of an instance of GossiPBFT, for which we already have the commit step. Then if you don't get lucky, and we have this Byzantine that doesn't communicate, and one of the correct nodes, for whatever reason, proposes a different block to finalize, and suppose they are not part of the same, so a different block from a different fork, then in this round, we cannot terminate, right? So we don't get a strong quorum of prepared messages for the same block. So every correct node in the commit step says, we haven't agreed, we should try again. So we go to a second round, and so the question is, who should change, right? Who should change their proposal? Should the one who proposes yellow switch to purple? So should the ones who propose purple switch to yellow? So the way we reach convergence in this is with a new step that is executed only from the second round on, that we call the converge step. So the converge step is a synchronous step. And in this synchronous step, what everybody does is still propose their preferred block to finalize. And with it, they execute a VRF ticket and they attach the ticket to this proposal. And then at the end of the synchronous timeout, every correct process looks at the messages, the converse messages they have received, and selects as the value to propose in the prepare step the value that is attached to the lowest VRF ticket. So in this case, the lowest VRF belongs to the yellow block. So even though he's the only one who proposes this block, everybody switches to yellow, and that's the one that gets. That's how we reach convergence onto agreement, and that's how termination occurs, and everybody decides yellow. Now here you can already see a problem, or somewhat of a problem that can occur. That process is the only one who proposed yellow, and then everybody switched to that proposal. That creates some incentives for censorship. So if you get lucky and there's this bias, so if you get in a situation where people need you to finalize, to terminate, and you want your block to be terminated, you can, selfishly just keep proposing your block until you have the lowest ticket, which will eventually censor the purple block. That's always a problem, censorship. In protocols like Filecoin that punish for inactivity, censorship is even more of a problem because you could effectively force punishments on correct processes and get them kicked out of the membership of the power table and eventually take over the power table, right? So that's why we set out the goal to also tolerate censorship against a very strong adversary. And the way we do that is with a new step in the first round that we call quality. So the quality step, it's actually kind of a flexible step that you can use. If you will to use this protocol, you could use it to enforce some other properties. In the case of our system, we want to provide the property of censorship resistance. And the way we do that is we run this quality step, and we basically only allow termination on values, deciding on values that pass the quality step. What does it mean to pass the quality step for us? It means that a value can only be decided according to a node if that value has been proposed by a strong quorum of quality messages. So in this example, only the purple block can be decided. It's either the purple block or nothing, because it's the only one that has been proposed by a strong quorum of messages. If another process were to propose yellow on top of the rational one that already proposes yellow, the only valid decision is nothing. Let's just not finalize anything in this instance. We try again in the next one. Hopefully there's a block that passes the quality value. So that's on the GossiPBFT protocol. Hopefully, if I manage to more or less explain this in 5 minutes, you can agree that this is not a very complex protocol to understand. But anyways, on top of that, as I mentioned, we want to provide finality certificates. The goal of that is to succeed verifiable certificates. The goal of that is for smart contracts to be able to assert the finality of some particular blocks, for light clients to be able to also assert the finality of a particular transaction or block without having to run a full node or sync with the chain or even other chains or layer 2s. And we do that with what we call the finality exchange protocol. So as I mentioned before, we run this special decide step. What the decide step, let me see. So in a nutshell, the verifier of a finality certificate needs to know the public keys of the power table and the previous output of the finality exchange protocol, so the previous finality certificate. And what the finality certificate contains is a strong quorum of signatures that are aggregated of the power table deltas, so the changes that occur to the power table as a result of the new finality certificate, and the finalized tip says that the finality certificate asserts finality for. And with that, and the knowledge of the public keys and the previous finality certificate, the verifier can compute the changes to the power table, compute the new power table, and also verify that these new tip sets are being finalized. Another interesting detail is that the power table deltas are actually truncated by 1 byte. That's because we don't want to represent every small change in the power table, because that will lead to a much bigger finality certificate. So we kind of accumulate changes to the power table and only represent them in the finality certificate when they're big enough. And so coming back to the simple example where Bob wants to deposit 4 fields in some exchange, initially it was 100 minutes. Then it went down to 5 minutes with the finality calculator, and now thanks to F3, he's gonna be able to deposit some fields in this exchange in about 15 seconds. Even more than that, the exchange doesn't even need to run a full node. You can just run a light client. Or if the exchange gets in some other way the finality certificates, it doesn't even need to run a light client, right? If Bob gives the finality certificates from the last one that the exchange knew up until the one that is interesting to Bob, the change doesn't even need to run a light client. So that's on the progress in terms of roadmap. As I mentioned, Finality calculator can already be implemented on your end. The design has been merged, so it's settled. But we're also working on providing the API functionality off the shelf in the Filecoin client. And it should be coming very soon. Then on F3, we have also almost completely finished the changes on the design of the FIP, the Filecoin Improvement Proposal. There's a couple more changes that will be coming this week, next week, but very minor, and then it will be completely finalized. And in implementation, we've been working for a few months already in the implementation, and probably integrating into mainnet and be released into mainnet end of Q2 with MV23 in a deactivated mode, and no later than a month from that being activated and having this fast finality that we've been talking about for so long. So that's all. Now fast finality for Filecoin is a reality, and you can use it as well to finalize your block, or even F3, you can use it for your longest chain protocol to also provide faster finality. Q. Any question? Yep.
I'm sorry, I'm a little bit confused about the EC by calculator and the terrain. Yeah. Like eventually we have F3 with like way fast.
Yeah.
Is the EC calculator just something that we use before F3 landed, or is it be the parallel running at the options in the future?
That is a good point. Once F3, so yeah, definitely the most usage of the Finality calculator will come up until the moment that F3 brings is in production. Once F3 is in production, the Finality calculator is already there, is usable by anybody with or without F3, and the API code will be there, which means that if for whatever reason you have an instance of GossiPBFT that takes 10 minutes, perhaps you can just call the API for the risk assessment that the Finality calculator gives you and say, look, even if GossiPBFT is taking a long time, I have a lot of confidence in this value. So, I don't even need to wait for F3. But yeah, in a normal scenario, F3 will finalize pretty fast, much faster than what the Finality calculator can give you. So you will probably not use it that much once F3 is in production.
One important part though is that, right, Gossip, sorry, Granite. It's the safety protocol while the ECE is a more liveness-based protocol, or it's the protocol that cares inside of liveness. So you might run situations where the safety protocol stops because it can't make progress. We don't expect should happen, but it might take there is rogue chance that it'll just pause for a while. And if that happens, you might want to set us finally. There's idea of GossiPBFT.
Yeah, that's the new name. And it is deprecated.
So I was the case.
Yep.
Because as the F3, if they're going to be integration, you will apply that. So you set the validator up to.
Yeah, no. So they use the same power table. So any storage provider that's registered in the storage power actor, which is the ones that make the power table now, but it's a different interpretation of it. So because we don't want to represent big, small changes to the power in the because we don't want to represent small changes to the power to keep the Finality certificates as succinct as possible. So there will be a more discretized representation of the power in the power table that is used by F3, but it comes from the same information. So from the same registry of storage providers in the storage power actor. So it will be almost the same in most cases.
Now, there's good chance in the future they will have it move towards you fix size committees. So right now it's all storage providers. Yeah. So, but as you have more storage providers, and then that changes, that will just not scale. Not by we have 3,000 storage providers right now, and GossiPBFT can deal with 5,000, I think. We think we're on certain problems.
Yeah, so the same way that you select some proposers in EC out of the power table, we might reach a situation where we select some committee out of the power table that F3 is using, which comes from the same data. Yeah. No worries. All right, thank you.